Welcome everybody here and in LA County. We are talking today about CNC System Internals, computer numerical control. That's what CNC means. It's a very, very complex controller that is fundamental to manufacturing, to say the least. And it's so complex that only a certain handful of countries have actually mastered the control over decades. And this will be the first, really, if you've mastered this control as a society or as a country, as you've mastered it as a professional, you've really reached some of the pinnacle complexity of control systems available out there. And today we'll just be kind of talking about the top layer of that, very, very high level. It's still very complex, and if you're not familiar with these systems, you probably won't grasp everything here, but we will continually circle back to it in various ways and dig down deeper and deeper. But yeah, so that's what we'll be talking about today. As it was last time. Oh, my name is Adam Cook, by the way, and I'm a core contributor to Build in Detroit. We are doing this presentation in collaboration with Society of Manufacturing Engineers, Chapter 153 out of LA County. And so they should be joining us via YouTube on the other side of the country. There you go. So a little bit of housekeeping to start with. June 14th, tentatively, is the next meetup we'll have. And in this one, so the last two meetups were sort of introductory topics to various things in manufacturing. This one will actually be looking at research that the Google Brain / DeepMind is doing in robotics. And I really hope to make, what I will do is I will take their research papers and try to distill it in a introductory, a nice format, a visual format. And I do have new animation software behind the scenes. You won't see it in practice today, but behind the scenes, so I can start animating some of these principles, some of these fundamentals, because a picture is worth 1,000 words, but an animation is worth 1,000,000. So we will be getting into some cutting edge research they're doing on the Google side of things. And there's a lot to look at there, and we really should be talking about a lot of that here in Detroit. And so June 14th, tentatively, same time, we'll be doing Saturday at 12 here in Detroit. We'll be doing that, but I got to see if the room's available and my time is available. But that's what I plan to do next time, and that should be really great.
That's a Friday, not a Saturday.
Is it on a Saturday, 14th?
Yeah.
Yeah.
No, it's 14th is on a Friday.
Oh, it's on a Friday?
Saturday's the 15th.
So
At least that's what I
may
get.
have to just
Just move it over.
yeah, thanks. Okay, so like I said, today's going to be like an introductory, very kind of messy introductory, I think, to CNC control. It's very a messy topic, so we'll try to get through it. But from that, I intend to create a series of lectures, which is in the top left corner there, CNC Internals and Programming. Okay. From that YouTube lecture, we'll have hands-on workshops. And while I was doing this presentation, a light bulb come on my head. why don't we do an introduction to Python programming for people who want to learn Python, but also want a practical application. What is a practical application? We could create a program interpreter. We could model motion interpolation and explore various algorithms in Python, and filtering and control modeling. All those things Python is really good at if you were building an actual control. And they also provide me an opportunity to introduce people who want to learn Python programming to actually some practical projects. These are very versatile, especially the first one, are very versatile. And then control modeling is a big Python strong point. But the other avenue that we could spring from this, that we will spring from this, is just if you are not interested in Python programming, but you're looking for the practitioner side, there's G-code programming, macro programming, and the PLC programming, which I talked a little bit about last time. And all those kind of play into the spectrum here of experiences around CNC control. So, I always get asked about book recommendations every time I do a presentation. I will be talking kind of, this is a good book. Let's put it that way. This is a very good book. It is a graduate level book, but it's the only book that I know of that actually gets down deep into the controls. And that was its purpose, if you read the foreword, about the authors lamenting the fact that nobody's actually dived down deep into these controls in a book format, a publicly available book. And this book was written in 2008, which means it's slightly outdated, but it's not. What the problems with the book are is it throws a lot of information at you, and the first and the second chapter and the third chapter are really great, and that's going to be applicable to every CNC machine you ever see out there. As it progresses, it gets highly mathematical. It talks about, I think, a lot of outdated concepts. It presents some code, but doesn't present it all, and I think there's a lot of gaps in there as you get from chapter 4 to the end, where if you're really not already a graduate level student, you're not going to grasp the rest of the book. You're going to get a lot of history, you're going to get a lot of parts, a lot of diagrams in the first couple chapters, but what we want to do is we want to fill in the rest. And we want to do it in a way that takes everybody along with us, which was the previous slide. You know, we want to fill in the code gaps that exist there. We want to fill in the algorithmic gaps that exist there. We want to fill in the modeling gaps that exist there. The book, in fairness to the book, it wasn't intended to be like a full, perfect representation of everything you needed to know. But we will make it that way. So I took some of the diagrams from this book. At the end of this slide deck, you'll see a few of them because I really liked them. But only some of this presentation will be directly from this. Video time.
Is the increments at which you're moving at?
If you've never seen a CNC machine before,
0.01, that's about as fast as we move, so we don't risk crashing the spindle.
that's why this is in here.
Now over here, you have your X, Y, and Z. Plus or minus doesn't matter, but you'll determine the direction with this dial. So X moves the table left and right, Y moves the table forward and backwards, and Z moves the spindle up and down. So I'm just going to move it till the edge finder is right behind this stock here.
right? So if you've never seen a CNC machine before, this is CNC machine tool equipped with a CNC controller. That's what's happening here. It's probably the most basic type. There's 3 axes and a spindle. Of course, CNC controllers can be used for more than just machine tools, but this is probably the most popular application. You have 3 axes, X, Y, Z, that are linear, and then you have a spindle that turns at a high rate of speed. You have a tool at the end of that, and it removes material. We'll see that in the next video of Fanuc Robo Drill, but this here is the human-machine interface. So this is what most people that are practitioners will interact with, right? It's got a hand knob to jog the wheel, emergency stop, power on, power off, display. So just an industrial computer interface specifically for this machine tool. Oh. So, I didn't want it to auto start. Note here in this video, this is why I selected it, the complexity of the cuts and the contours. The individual on the last video didn't do any cutting. This one is cutting, and notice the contours, notice the complexity of what's going on in a lot of these setups. Some of these are what they call 5-axis milling machines, where there's actually a rotary table that moves in 2 different rotary axes, plus the 3 linear axes, X, Y, Z. So there might be A, B that are rotary, and then X, Y, Z that are linear. This clicker's not good for videos. I have to rethink that. Machining some aluminum here, looks like. It's a 5-axis milling machine there. The tool changer there, the various tools can be mounted, grabbed by the spindle. Okay, so this is getting off on a little bit of a tangent, but not only does a CNC controller at the end of the day is a controller. So it not only controls the physical functionality of the machine tool itself, but it can also output data. And in that configuration, it can support what we call flexible manufacturing, some kind of industrial Ethernet being used to a separate control system, a flexible manufacturing. I got a video on the next slide that shows that. But you can actually pair these controllers together, tie these controllers together to do flexible work. You can schedule jobs in each of these machines, and together they can essentially talk to each other and schedule jobs in a flexible configuration. So this is another. We will have a separate series on industrial Ethernet, which is interesting in its own right, but it shows the versatility of this control, in my opinion. Probably one of the more popular. There's a track with a carriage, and behind this carriage there'll be a series of shelving units that'll hold pallets of fixtures, and you'll see that in a minute. kind of get a sense of the flexible nature of this system right now. Right, we have two loading stations here where either a robot or a human can load a part. We have fixtures here against the back that either have parts loaded into them or are waiting parts to be loaded onto them. These are the CNC machine tools there. And the controllers on each of these machines essentially talk to a scheduler here that can manufacture parts with the lights off or on a schedule, or if there's incoming orders from somewhere else, it can plan for that. You see they can rearrange this thing in all kinds of different configurations. That's a part that's been machined in a vise already. So the operator would unload that and put a blank part back in there, and then that part would go to one of the machine tools based on the schedule that is set in the FMS. Putting a fixture into the machine tool there. And there's your lights out operation, basically. So, all right, that was kind of a tangent. Let's get back on track. 3 videos ago, we saw basically the human-machine interface, a pendant that hangs off the side of the machine. It's got, the purpose of that is for the human operator or service technician to interact with the machine, input data, check machine status. Various values will be surfaced. There's various information surfaces on this human-machine interface. It's just like your laptop computer or your desktop computer. Basically, it has keys, and this one just happens to have functions that are necessary for CNC machining or operating a CNC controller. All right. There's also a concept of a programmable logic controller, sequential control throughout the machine. It reads in sensor input. There's sensors all over the machine doing various things. It runs that against a logical program and outputs actions based on that. And the CNC controller, this is an integral part of the CNC controller, and the CNC controller can command the machine to do discrete physical actions, and essentially the machine needs to understand if it can do those things at the appropriate time. And that's but one of the, so I have here, if you look into it, it's quite, the ladder diagram for a vertical machining center, which if you've never seen this before, it can be quite intimidating, but it actually, and it is quite intimidating, but that is an integral part of, and again, we will have to break that out into a separate session, but understanding that is integral to understanding CNC machine controls. And then we have something called the numerical control kernel, which really is, uses numerical methods and algorithms to convert high-level motion instructions into actual control and into actual physical work at the end of the day. And this numerical control kernel has a very intimate relationship with motion control, the motion controller, which is also part of this. Okay, so if I ripped out the guts from a CNC machine tool and put it on the table, this would basically be the core of what you need to see, basically. If you're doing a workshop or something, you should probably have this laid out in front of you. This is more logical than physical nowadays. In the past, and I brought another thing here if we had some more people made, but this is a Mitsubishi CNC manual from 1982. back then, we didn't really have powerful computers. So a lot of this was physical. These were individual devices mounted in a cabinet. And it was quite complex, but it was all hardware-based control. And there was some software, but it was primarily a hardware affair. Nowadays, a lot of this is collapsed into a more software-oriented affair, and you don't really have discrete hardware associated with these things. They're all kind of collapsed into one. Underneath that, architecturally, they're still separate to some degree, but we don't require the physical components anymore. And I would say that's probably, if you refer back to the book that I had originally, that's probably where it gets off on its main tangents, talks about a lot of hardware-based control. For some that may be, in my opinion, for some that may be beneficial, but for I think for a lot of applications, it kind of gets off onto a tangent. Like I said, the NC kernel will have a very intimate relationship with the motion controller. At the end of the day, a command, a signal, will be sent to the motor, which will cause it to turn, thus turning a ball screw, thus moving the axes. And if this was a spindle, it would just turn itself. And on all of these motors, there's an encoder which spins along the shaft, mechanically, along the shaft, and it gives a feedback signal. Okay, the motion controller will then compare these two signals and adjust in an accumulator the feedback, the motor accuracy. And that's essentially what happens, or this is essentially a visual description of a servo motor arrangement. Okay, so there would be 4 motors, like I showed on the last. There would be the X, Y, Z motor, and then a spindle motor, and they would all basically conform to this. It's a little bit more complex in practice, but this is as high a level as you can go with that. There's some concept of command, actual mechanical output, feedback, comparison, adjust. So, and the NC kernel is an intimate part of that. So, let's talk a little bit about, let me get caught up here, actually. There are, we will touch on it in more detail later, but there are two. What I'm describing here is essentially a computer. It's an industrial computer, but it's a specialized computer at the end of the day. And this computer features what's called a hard real-time operating system. It may have Windows on it, it may look like Windows, but architecturally at a lower level. It demands more than what Windows can provide. Windows is a consumer operating system, and we need something more industrial. And the 2 platforms that I think are becoming fairly popular, are already very popular in the CNC space, is RTX 64, and then there's TwinCAD. And I'll probably be spending a lot more time throughout later sessions and workshops talking about TwinCAD than RTX 64. Just because TwinCAD's a more complete package, but they both essentially work the same way. And that is you have a multi-core processor. On one of the processors, there's Windows, and the other processes are taking over for something special, for real-time, hard real-time work. Okay, and this is from the RTX, website here. You have a piece of software here that hooks into the kernel mode of Windows 10, of the host operating system, takes some cores for itself. Of course, in this case it's 3 cores, and then there's the windows on the 1 core. And then basically from there, you have a dedicated set of APIs and you have a Windows-like interface that you can write applications. And to the user of these CNC machines, in a lot of cases, it looks like Windows staring back at you. But the applications are written against an API, and the lower level parts of that machine actually have something very special going on. And we'll talk about the importance of that later, but this is basically an integral part of it too in terms of software. This is the lowest level part of the software, and you have to know that this exists. And if you want to write software for CNC machines that runs on the actual machine itself, on the actual controller itself, you have to understand this arrangement. Okay, so a bit of history. In the beginning-ish, a long time ago, there were punch cards for machines, and we fed these into the machines to do very platform-specific instructions. The machines had no portability in general. The punch cards were manually punched out, and the sequences expressed on these punch-outs would cause this specific machine to do something automatically. Okay, very, I would say, labor-intensive process. One of my first things in my career was converting punch cards into actual G code, which is what came afterwards. It was standardized by ISO 6983, and we'll look at a little G code in a minute, but this is probably the most popular type of program for the CNC machine tool these days. Still, portability is somewhat wonky. If you write G code for a Fanuc machine, it may not work exactly on a Siemens machine more often than not. There's a lot of proprietary codes in there that do specific things if your machine is fairly exotic. But this was basically the evolution, if you will, of that, which it got nicer. You know, this you can't really read. If you know how to read and write G code, you can kind of read this, and it can kind of be portable, but not really, but it gets you close in some cases. And then we have the newest kid on the block, which is STEP. Basically, the idea, whether it's adopted in practice or not, it's, in my opinion, it's lagging a bit on adoption. But the idea is you have a CAD system that you are creating parts into. You export something standardized to ISO 10303 into your CAM system, computer-aided manufacturing, in which case you will basically provide manufacturing instructions, machine tool instructions, that'll be exported with another standard to the CNC machine. And we'll look at that a little bit more in detail in the slide after next. But the idea here is that there's a standard between the CAD and the CAM system, and there's another standard between the CAM and a CNC machine, and therefore it should be somewhat portable, more portable than ever. In practice, like I said, I think it's been hard going. In a lot of cases, some have adopted this. Some government agencies have required some of it in pieces, but that's where we're supposed to be going in any case. But all right, so if you use CAD and you model a 3D part, at the end of the day, to manufacture the 3D part, you need a drawing or something. And the traditional method is to make a 2D representation of the part and decorate it with a bunch of geometric tolerances and dimensions and everything, and show how the part should be manufactured, in which case you go from CAD to a 3D model, but off to the side here is your 2D drawings that I just showed. So those are here. You go to the 3D model. The 3D model goes to your CAM system where, again, you're going to specify tools to be used, feed rates, the tool paths themselves. And you're going to take the 2D drawings that you produced and that's going to influence what you input into your CAM system. Right? And then there's a post-processing step. So there's a compiler embedded in the CAM system that knows what language your CNC machine speaks in terms of G-code, what dialect it speaks. And it's going to post-process what you do visually into G-code, and that's what you're going to put in your CNC machine to do actual work. Now, what's the problem with this? The problem is the 2D drawings you had over here. Essentially, there's a information loss. This information was not directly traveled to here, and so someone could have read the drawings wrong. There could be changes in the CAD model that get expressed on the drawing that may not have been incorporated through this workflow again, and then all of a sudden you're manufacturing parts that aren't to spec anymore. Or, you could have just read the drawing wrong and made the CAM, originally wrong, So the idea has been to evolve into this. Again, adoption to me has been low or uneven in industry, but this is where people would like to go. It's make a 3D model, and instead of making 2D drawings, you express all the product information on the 3D model itself, as shown here. This is NX. It's a certain type of CAD system, and you can see all the dimensions and geometric datum, surfaces, and everything specified here on this 3D model. And the hope is, so what you saw there was product and manufacturing information. The model, the 3D model, and the practice of doing that is called model-based definition. Okay, and so the idea here is take your CAD system, have this rich model. You don't have the 2D drawings over here anymore. Have this rich model, have a CAM system that already knows natively what capabilities are in the CNC control target, and you can specify tools against that. It has all the manufacturing information that travels along with it. So you don't need this separate reference. You don't need these artifacts over here. Everything travels as a unit. From here to here, you specify manufacturing processes associated with your part, and then it goes into the CNC machine. The CNC machine understands that natively as the CAD and the CAM system do. And so you lose a lot of complexity, in theory. I haven't seen too much of this, but that's what the workflow is. And we may not do it according to step, but we will explore 3D models in our own neutral format as an educational experience. But I think this has a lot of promise. I think the logistics of getting it out in industry have been uneven, though. There's a lot of coordination required to get this done, and a lot of competitive interests, I think, and it's been slow going. But that is supposed to be the future. All right, let's take this apart piece by piece. We have the human-machine interface here. We have generally an industrial PC that is non-real-time, that governs this display here. And on this display, typically, the core functions, I would say, are the digital readout, which is the XYZ here. There could be an A and B axis that do degrees, various operational information, parameters, machine parameters, various settings that are associated with the machine, tool settings, what tools are in the machine carousel, the tool carousel, what lengths are they, what diameters are they. various things like that. And then service and diagnostics, if there's something wrong with the machine, if you need to change a PLC program associated with the machine, this information surfaces that as well. So what's on the screen is the G code. We finally arrived at the G code. This is just a sample program of G code. But this is how it all kind of looks. I would say this is fairly portable across many machines, but there are specific differences that we will not go into because I really don't know them in exhaustive detail what the differences are, but this is how G code looks. Right, so let's break this down a little bit more. All right, these are 2 lines that I've extracted from the previous screen. Okay, we have a concept of a block. Some people call it a line, but it's actually a block. And then that's a block too, right? So they're all block, 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 block. All right, we have a concept of a word. Right, there's a space between the word, we have that. We have an address, which is a letter, and we have a number or a value that comes after the letter. And that's pretty much how it looks across the program. Okay, the same sort of word, address, number, block by block. Okay, this won't be an introduction to G code here, but when we get to that workshop, this table's actually cut off. There's actually quite a few more letters that you can have in here, but these are what I consider the primary letters, addresses associated with the machine. But yeah. Okay, so that was, let's say, the HMI part. Now let's go on a little bit to the PLC part. Okay, you have a machine in front of you. Let's say you issue a G code to change a tool. If I can go back to it, there's a tool change code that usually specifies in its number, usually specifies a slot that the tool is in. And when you issue that code, okay, you want the machine to mount that tool in the spindle, usually automatically. So you want the machine to perform a physical action for you, a discrete physical action for you. But how does the controller know that the spindle is in the right position, for example, to accept that tool? How does it know various other conditions that might be surrounding that tool change process are in the correct spot? All the switches are closed that are necessary to protect the machine and to make the tool change successful. So what the machine is doing is it's reading various switches and sensors on the machine. And it's saying, if all these conditions are satisfied, go ahead and perform the tool change. But only if those conditions are satisfied. And again, if you look at, this is a very simple, if you looked at this machine in practice, it would be what the individual was operating on the first video. It's a very visually simplistic machine, but there's actually quite a lot of sequence logic going on inside the machine to do various physical things. A lot of checks that need to be satisfied before something happens. And a lot of sensors all over the place and a lot of actuators that respond to the PLC output. Okay, so this is a very integral part. It really can't do, the CNC machine is worthless without this part. So, like I said, this part, I'm breaking everything out physically here, but in general, it's all been sort of collapsed sometimes into a single package, but this is just for illustrating. You have a PLC program that's standardized. Well, I should say the languages are standardized. The actual PLC program, again, it has varying levels of portability from PLC to PLC. There's some tools that help with that, but you basically specify your PLC program, you compile it, you load it into the PLC, and again, there's input sensors and then there's outputs. And all this is connected to the numerical control kernel somehow. Why? Because the numerical control kernel, at the end of the day, is what's connected to the HMI, which is issuing the command. So these have to have they generally have a shared memory address. The NC kernel writes to the shared memory address, and the PLC reads from it, and the PLC writes back to it again. So all these things work together. If they all work together, they all have to talk to each other. So this is how the executor works, basically. This shows how the NC kernel part is connected to the PLC. Basically, you're going to read from the NC part may have written some data into the addresses that the PLC can also access. We have to read the machine interface. We have to understand the status of all the sensors around the machine. Okay, then we execute the program, and then we write data out to both the NC memory and to the machine interface, essentially writing it out to the physical world. And all this repeats very fast. This cycle is very fast moving, milliseconds, if not smaller. Continually does this, reads memory, reads the machine, performs the PLC program, and then writes out. And that's, you don't see it, but that's exactly what's happening inside the PLC part. And this is all real time. This is all real time, which we will get to in a little bit. Actually, we'll get to it right now. So, this is another book recommendation. Again, a graduate level text. The book assumes that you are already acquainted with operating system design from a computer science standpoint. But in terms of, I think, the most accessible, both in content and the fact that it spends quite a bit of time on Linux, the Linux operators, which is of course freely available, unlike a lot of the other hard real-time operating systems. Linux is readily available, and I think in that sense it's a good book. If you try to read it and you don't have a good understanding of operating system fundamentals from a computer science standpoint, you probably get lost. But I think out there, on a difficult topic, I think out there, it's probably one of the better texts on real time. And of course, we're talking CNC, we're talking about using a real-time platform operating system in the context of CNC controller. Here it's used also in aerospace applications, or anything that is mission or safety critical. Like your laptop here wouldn't be running a missile silo. You would need something more industrialized than that. That's where the hard RTOS, real-time operating system, comes in. So just blowing this up again, we have a CPU. It's one package. A processor is one package, but it contains 4 cores in this case. It can have more cores than that. One of the cores is dedicated to Windows, and then there's something else, either TwinCat or in this case RTX 64, that takes over the other cores on the same package. And so Windows no longer sees these cores anymore. For all Windows knows, it just has one core now, and there's something else happening alongside Windows. And that's expressed visually here. Okay, so a hard real-time why is a hard real time? I keep mentioning this. Why is it important? Because at the end of the day, when you're running a machine, there are safety issues associated with if a machine cannot respond to a situation in a well-defined manner, you will either get a safety issue. I don't care, it could be an airplane, it could be a train, it could be a medical robot. There are certain things that happen that a machine needs to respond to right away in a predictable manner. And it needs to perform things in a predictable manner, or people will die or get hurt. Or, less dramatically, you'll have bad part quality, or you'll have parts that are coming out of the CNC machine that are unpredictable. Essentially, they'll be so the machine cannot properly accomplish its task, and so you need this special operating system to run your software that has these three traits. There's more traits, but these are the three primary ones. A low, well-defined interrupt latency if the operating system or a piece of hardware interrupts a task. You want to know, as a designer of the system, as a programmer of the system, you want to know that it is both minimal and it is well-defined, what you can expect from it. Okay, that's the same for a context switching. Okay, between tasks, you have various tasks on an operating system, and the operating system needs to change from one task to another. Just like we change from one task to another, there's a period of latency, right? We don't instantaneously move on to it. We don't drive a car and instantaneously start reading a book. There's a delay, right? We want that to be well defined as well, and it supports, again, interrupt and task preemption based on priority. So if something comes up, if there's a critical task that needs to be accomplished, all the other tasks can be put on the back burner and that task can be addressed immediately. These are things that the Windows, your vanilla Windows or Mac OS or your Android or your iOS phone don't have to deal with. They focus on energy efficiency and performance of the applications. Here, we want something very, very, very definable. We're trying to make a machine here that, not only life and death associated with it, but part quality. Okay, so we need these well-defined things that Windows cannot provide us. So if you look at, if you just have a Windows computer, right, there's a concept of a task and it starts running. Could, maybe Microsoft Word or something, right? Another task starts up, maybe you open up a web browser, right? It starts running, putting this task into a wait. Okay, you can see that this bar here and this bar here are bigger, this bar is bigger than that bar. Now maybe this task gets done, it stops waiting again, there's a context switch delay, latency, and then it starts running again. It returns back to there could be a bunch of tasks that you don't see be happening behind the scenes in Windows or on your iPhone, and this is kind of how it looks. The scheduler, the thing that starts and stops and pauses these things, is primarily concerned with performance of the applications and of energy efficiency. Okay, so it really, without getting into too much detail associated with it, it really juggles things around as it needs to accomplish those goals. And if your computer gets unstable, if your iPhone needs to be restarted, your computer gets unstable or something, it's not the end of the world. The plane's not going to crash, the robot's not going to, kill somebody. It's just a consumer device, right? And there's a representation for what we're working on. We need something more well defined. And so again, Core 1 is taken over. Let's talk about a 2-core processor. Core 1 is taken over by Windows. What happened on the previous slide happens in here again, no problem. This is on a separate core. It can be Windows. Windows can't see this core, which is in this case taken over by TwinCat platform. Okay, now we have tasks and we have priorities associated with tasks. The lower number, the higher criticality the task is. Okay, with Windows, if you're programming a Windows application, in general, you don't really care about what the scheduler is doing. You don't really care about what's happening behind the scenes. Windows can do its thing, and you're just making a consumer or a business-oriented application, and Windows does its thing, and as long as your application is stable, you don't care. In a real-time setting, the programmer is now responsible for managing the scheduler, managing the programming of the applications such that they can be supported by the real-time platform. It's probably the best way I can describe it. Here you have very little control, maybe you don't want it. Here you have all the control, or a lot of control. And because you want things in your machine to happen in a certain way, and you want those things to happen predictably, and sometimes those things really need to happen when they need to happen, and so you have to have that kind of control that you don't get in a Windows environment. You can kind of see it just, So, each of these blocks are roughly the same height over time. Okay, there's the concept of a cycle time or scan time in PLC, and you have to keep your tasks, you have to write your programs, you have to write your tasks that keep inside of those windows. If your tasks overrun those boundaries, you're going to get undefined behavior in the machine. What good is a machine that has undefined behavior? It's not good at all. You throw it in the trash. I mean, if you put something into a machine, you want it to be deterministic. If you tell a machine what to do, you want the machine to do that, and you don't want to go back to it tomorrow and say the same thing the machine does is something totally different. So you need that kind of control. There's no value in a machine that doesn't have that kind of control. In bringing it back to the CNC, you can see here that motion control has the highest priority probably in the machine. It's actually doing the physical work. And you have the interpolator, you have the interpreter that interprets the program, and each of these shares a discrete time block. And the challenge at the end of the day, the challenge with programming a CNC controller is that you have to, again, design your system. You have to design your architecture to keep these actions well defined in their boundaries. If they start bleeding into each other, you're going to have a machine that doesn't work. Okay, I don't think we have a lot more to go. Yeah, just a couple more slides. So, three main parts that we haven't discussed, I would say software parts, software applications. The interpreter, okay, so you're giving the machine tool a program of text if you're using G-code, okay. The machine needs to interpret that program, it needs to understand that program. It needs to take it apart and store the data in its internal memory structures, and it needs to essentially read, you're giving it a document, the machine is reading that document, and it's doing something with that document. It's converting it into its own internal language. Okay, you have the acceleration, deceleration control. So if you saw on the second video, the machine or the tool, the end mill, producing quite a complex contour in a machine, in a part, quite rapidly. The three things you need to do that is you need the position, which you are specifying generally indirectly, let's say by the G code. You're specifying a start and end point, usually maybe some control points. You need the velocity, which you specify directly or indirectly in your G code program, but what isn't specified is acceleration and deceleration control. So what you saw, the G code was separated into blocks. The problem there is if you have a particularly complex surface that you're machining, what you don't want to happen is that the tool machines something in one block and then jerks, and then machines something in another block and jerks around all over the place. So what you want to do is you want to have when you're operating at those speeds on the machine tool, a very fast machine tool, there has to be a way to sort of manage the acceleration and deceleration of the tool itself such that the part quality is good. It also protects the machine itself. A machine that's jerking around while it's cutting something is going to destroy the tool, it's going to destroy the machine. So that is an essential control, a particularly complex part of the machine that few recognize that it's happening, but that is actually happening. You specify a start and end point of something and a feed rate, and you have to, you want it essentially smooth. You don't want it to be jerky as it's getting from point A to point B. And then we have interpolation, which is essentially, there's linear and circular. Interpolation is basically in G code, if you specify the start and an end point of something and maybe control points or something, what are the points along that path? Okay, so you've just specified the start and end point. The machine, at the end of the day, and the motion controller needs to understand exactly what the path is. And depending on the path, and we'll see one particularly complex path at the end, I think. Yes. Depending on what that path is, it may be quite complex. It may not just be like a straight line. It may be a surface even. So you need to needs to be a function in there to take your incoming data and specify all these little points along the contour path. Now this I did take from the book. I think it's particularly well done. The only problem with it is, and you'll see in the next slide, is the acceleration, deceleration control. It's not wrong. What used to be done is you had the NC program, which you can see up there, okay? The HMI loads it. You have the interpreter, which we just discussed. It's basically talking about endpoint calculations and all the various tool changes and things you need to do with your machine. Okay, then you have the interpolation, which I just discussed. Then you have the acceleration and deceleration control. And then you have the motion control, the actual movement of the tool. Okay, and this is essentially done, I will say very rapidly, but it's actually a lot more complex than that, and we'll see at the end what I'm talking about. In modern, this is an older, I would say, workflow. What's happening inside your machine. What happens in reality, you can see that the interpolation is before acceleration and deceleration control. These days, with modern computers, it's actually at the top, and we have a rough interpolation step. We map that interpolation data to each axis, and then almost always, if you're doing a high-speed machining operation, you'll need fine interpolation, and then we have the motion control step. So the acceleration, deceleration control comes before the rough interpolation. That was only made possible through the advancement of the computer itself. In the past, we were limited in being able to do that. And I won't get into it, but there's a reason, there's a data structure and a memory reason for that. But yeah. So in future workshops, we will be exploring this acceleration, deceleration control, the rough interpolation, fine interpolation. There's actually quite a bit of strategies available for interpolation, depending on what's going on. Sometimes CNC controllers can adapt a certain interpolation strategy based on the feed rates, how fast your tool is moving. Sometimes it's limited by its own capabilities. Sometimes the machine requires, just by its, if you have a 5-axis machine like we saw, which has 2 rotary elements on the table and then 3 other axes, sometimes it requires a sophisticated interpolation strategy. You're making very complex parts very quickly, and you want a very smooth surface. Okay, so you need very fine, you need different interpolation strategies associated with that. And each one of these, when I used to do the workshops, each one of them took up a day. The interpreter, the acceleration control, and the interpolation strategies. And of course, all those software things are embedded into, are integral to a control system conversation, right? So there's an actual motion controller. It's taking in all this input data. It's giving back feedback to the NC kernel, and so it's a very intricate ballet. This does not do it justice. Let me show you. This does it more justice, but even this is not complex enough. I took this out of the book too. There's an interpreter, they call it a ring buffer. There's various other strategies to hold this data in memory. There's a look ahead, so the CNC control looks ahead a certain number of blocks into your G code. 1,000 more, doesn't matter, some machining operations, a lot more. And from that, it performs some kind of acceleration, deacceleration step, a rough interpolation, right? It maps it to your axes, and you can see all the activity happening in here. All the activity happening in here. And what I cut out from this presentation was, once you get to this point here, there's actually a whole lot of control theory that's associated with this to make it actually work, to actually move your tool and keep your machine stable. I mean, there's stability conversations, there's differential geometry conversations here, there's calculus, of course, and it'll take a lot of time, but for this series to be successful in the long term, we'll have to break down those individual parts. Let's go back one. So this is the interpolation I'm talking about. If you have a die that has a kind of a wavy surface, right, and on your CAM system you make control points to make this curve. Okay, that's great for your CAM system to make a visual picture of it, but at the end of the day, the CNC machine needs these black points, these interpolation points. Okay, and there's a strategy called NURBS, curve interpolation, that basically the point is to find all these black points by but also minimizing the error between the points. That's it.
Excellent.
Good or too complex? Any questions? Any questions online? Let me see about if I can access it. Pretty complex? Somewhat familiar to you?
No, I mean, for me, it's, I was at GM Design Center for 5 years, creating surface geometry, so I understand,
Right.
the interpolation concept, I understand if you understand how geometry has to be created, also get a picture of how the machine tool has to, recreate that same interpretation in the controller to be able to manage it.
Right.
And it has to look ahead because machine tools are cutting at those feed rates. Like you said, they have to accelerate and decelerate just to hold a reasonable tolerance,
Right.
at those feed rates. And then that's why you rough things out, and then you come back to interpolation. And there's always a dependency on the servos and the relationship to, on a 5-axis machine tool, which is the slowest servo, in order to do the rotary action, I have to coordinate that with the linear action, and make all that a concrete path that represents the part.
Right.
All those slew rates have to be harmonized, right?
Should have wrote the initial forward into the. No questions online? I don't think, let's see if the chapter contacted me. Ron over there is. Okay, well, I think that might be it for today. Thank you for joining, and we'll see you next month. Thanks.